Okay. Good morning, students. In the last two classes, we saw the basic model of Turing machines, a very simple model of computation with infinite tape as a memory. And we showed that these Turing machines are not so weak. In fact, we showed that many other models of computation which are much more complex can all be simulated by this basic Turing machine. So these are called robustness properties, and in this we showed that Turing machines could simulate multi-tape Turing machines, or they could simulate multi-counter automata. There are these more sophisticated systems of computation such as Gödel's mu recursive functions or Church's lambda calculus. It can be shown that even these can be simulated, their computations can be simulated by Turing machines. So Turing machines are rather powerful, and in fact there is this Church-Turing thesis, which is based on a philosophical argument, which says that Turing machines can simulate any mechanical system of computation. That is, they embody a rather essential notion of what is mechanically calculatable, right? So this was the Turing's idea, defining a model which captures the notion of mechanical computation, right? Now we know there are two kinds of Turing machines. There are Turing machine, when given an input, can do one of three things. It can perform a series of steps of computation and either reach an accepting configuration, in which case we say that the Turing machine halts and accepts the input word with which it begins computation. The other possibility is that Turing machine on given input can reach the rejecting state R. Thus, we say that Turing machine halts and rejects. But there is a third possibility. Turing machine can keep on, going through different configurations, an infinite sequence of configurations, none of which is accepting or rejecting. In this case, we said that the Turing machine loops on the given input. Now, this is a little bit like a program which does not terminate on some given input, And so this Turing machine has these three properties. The set of words which are accepted by the Turing machine, that is those inputs on which the Turing machine halts and accepts, is called the language of the Turing machine. And languages of accepted by Turing machines are called recursively enumerable languages. There are a special class of Turing machines which on any given input will never loop. For every given input, it will either halt and accept or it will halt and reject in some finite number of steps. Such Turing machines are called total Turing machines, and the language is accepted by this special class of Turing machines are called recursive languages. So clearly recursive languages are a subset of recursively enumerable languages. Now the question that naturally arises is why design a Turing machine which does not halt? Maybe it seems like a rather inefficient design where on some inputs the machine keeps consuming electricity, never finishing its job. It's better to design a more efficient program for the same task which will always halt, either accepting or rejecting. So maybe every problem that we are interested in solving mechanically should be solvable by total Turing machines. And so the question arises, are there special problems which can actually be solved by Turing machines which are not total Turing machines? That is, are there languages which are recursively enumerable but they are not recursive? So this is a very, very, very deep question, and that was one of the questions that Turing asked. Now, why would we define these Turing machines which are which may not halt? See, these are the Turing machines which try to find answers by searching. So for example, natural numbers can be written as strings in unary as a sequence of zeros. Number n can be represented as a sequence of n zeros, and maybe we can search for some natural number with desired property by systematically searching the list of natural numbers, generating and searching for list of natural numbers. Now this search may never finish if no such natural number exists, but if it exists, the search will finish. So such open-ended search kind of programs will constitute recursively enumerable languages. And question is, for such languages, is there a better design of a Turing machine which will always halt? So the question is, are there languages which are RE but not recursive? And then there is a larger question. Are there languages which cannot be recognized by even by any Turing machine? That is, the languages are so complex that no mechanical system of computation can embody, except those languages. That is, if you give a word and ask whether the word belongs to that language or not, no mechanical system of computation can determine it. So, are there languages which are not RE? These two important questions, RE but not recursive, and languages which are not RE, are something that we seek. It's a deep intellectual quest. Now we saw that actually total Turing machines can recognize lots and lots of useful languages: a raised to n, b raised to n, c raised to n, ww, a to the power a to I, where I is some power of 2. So how do we find out there are languages which are recursive? In solving these questions, these were the key questions that Alan Turing explored in his pioneering work, which founded this field of theory of computation and theoretical computer science. It is for this that he is sometimes called the founder of theoretical computer science. Many ideas in his Turing machines have inspired later day computers and programming languages, but he went farther than just defining this model of Turing machine. He wanted to find out if there was any limit to mechanical computation which was equivalent to limits to what can be calculated by his Turing machines. And the key ideas in answering this kind of questions were three. He defined a very specific kind of Turing machine, one specific Turing machine called universal Turing machine. Now this is a Turing machine with some startling properties. So we shall see what is universal Turing machine. Then he defined a problem called halting problem. So we will see what is this halting problem. And finally we will prove that halting problem is a problem which cannot be solved by any computer in the world. That is, it cannot be solved by any Turing machine, no matter how sophisticated that machine is. So we will prove the undecidability of halting problem. This is my quest in next 2 lectures, but let us begin. Okay. So universal Turing machine. Universal Turing machine is a Turing machine. It is actually a machine which takes as input another Turing machine M and an input to that Turing machine M. So, basically our aim, like in a compiler, you are given a program and you want to do something with that program. Compiler is itself a program which takes another program as input and maybe optimizes it and converts it into machine language, right? Like that, your universal Turing machine will take a Turing machine as an input. It will also take an input string X to be processed by this Turing machine M, and it will try to mimic this one machine UTM will try to mimic the behavior of M on input X. So you see, why is such a machine interesting? Well, normally every Turing machine is different. It is described by a different M tuple and it will have to be constructed by a different kind of electromechanical assembly, right? Different Turing machines will have different number of states, so you will have to construct a machine with different number of flip-flops which represent the states, and each Turing machine will have a different table of computation, the transition rules, so you will have to build different kinds of logics for it. So potentially there are these infinitely many different Turing machines that you will need, one for every problem that you want to solve using some sort of mechanical computation. Instead of that, what Turing said was, I will build this one standard model of computer called UTM. Okay, and this UTM will take some sort of description of my Turing machine which I wanted to simulate as input. It will also take the input to that Turing machine which I am simulating, and then it will start mimicking this machine M on behavior of this machine M on input X. Okay, that is what it tries to do. So in other words, it's like a Turing machine interpreter, and this is similar to a Python interpreter which is written in Python itself. So let me make explicit these ideas. Let me add a page here. When you say Python, on your computer, when you say Python say Python 3, this is the version of 3, and you give it a program called foo.py. What happens is, this Python 3 is a program which is available on your computer, on your laptop, and what you give to it is a file called foo.py. Okay, and what this program Python 3 will do is, it will try executing the statements of this program foo.py. Maybe instead of foo.py you have a program called factorial.py. Okay, and what it will do is, this factorial.py, when it executes, it will ask for an input number n, and then when you give it some number like 3, what it will do is, it will do step by this Python program. This factorial program says how to calculate the factorial of this input number 3. Okay, the answer is how it will behave. It will first take this number 3 and multiply it by the decremented number 2's factorial, which is equal to 3 into, so 3 factorial is simplified to 3 into 2 factorial. This is further simplified 2 into 1 factorial, and which is equal to 3 into 2 into 1, and which is then simplified to 6. So this is what your factorial program will say. And but what is this Python 3 program doing? Factorial program is doing all these calculations step by step like this. You are running a program called Python 3, to which you have given another program called factorial. So what Python 3 does is, it understands what this program factorial.py does, and each statement within this factorial.py program, it will try to mimic. So this Python 3 program tries to mimic factorial.py program on this input 3, and so it will also produce this answer 6, right? So Python 3 is an interpreter for Python programs. What does that mean? It takes as input a Python program and some input which is to be given to that Python program. And what it does is, it carries out the same computations that this Python program will do on that input, right? Now you can't give a physical program. Program is something that is loaded in the memory, it uses CPU and it does computation. You cannot directly give a program to another program. What you do is, you type this factorial.py program, as a sequence of characters using your text editor, and the file of this containing this textual version of this factorial.py program is given to Python 3. So what this file factorial.py contains is the code of Python program. Moreover, this factorial.py may itself take its input from another file. So the input is also given in some code form in some file. So basically, when you write an interpreter program, the interpreter program takes the code of the program that you are trying to emulate and the code of the input, and then mimics this combination. So let me state this again. So this is, your universal Turing machine is Turing machine interpreter, right? It itself is a Turing machine, but it interprets other Turing machines. It takes, the description of the Turing machine M in some coded form. So remember, our Turing machine can be described as the 9-tuple. What is its set of states? What is the input alphabet? What is the tape alphabet? All this list of 9 things can be given as a code, as a string to this universal Turing machine. So I will denote the code of a Turing machine M as angle bracket M. Whereas M is actually the physical mechanical realization of that machine, which can actually run. It will contain those flip-flops and circuits, the input head which will go and read over the tape. But this is just the description, that 9-tuple description of the Turing machine, right? So this idea is clear. Moreover, this UTM not only will require this M, it will also require the input X on which this M works, right? So because this Turing machine M, will take some input on its tape and then start executing, we must provide to UTM both M and X. So in other words, what UTM, is a Turing machine. Firstly, remember, UTM is a Turing machine. On its input tape, what does it take? It takes the code of my machine as well as the input code of the input word, separated by this special symbol called hash. So this is what will be the input string given to the Turing machine. And then what does the Turing machine do given such a pair? So if you had a Turing machine which was calculating factorial of x, then you would give the description of that Turing machine. And if you wanted to calculate factorial of 7, this code of 7, which can be written as 7 zeros if you like, separated by hash, this is what you will put on the input tape of this UTM, and then you will start this UTM just as you would start that program Python that I told you. Python was the interpreter for this program file that you gave. Similarly, you will start UTM, which is the interpreter for this Turing machine M and this input X. And what does your UTM does? It mimics the behavior of M on X. Now M, M on X will do what? It will start with the initial configuration on this input string, and it will do step-by-step computation. Now each one step move of this machine M on X, will be mimicked by this UTM by one phase of its behavior. Remember, this one phase may require several steps of computation, but it requires a finite number of steps, and it will finish. And at the end of that phase, it will have the same effect as this one step move of M on that X. So remember, we simulated K-tape Turing machine by a basic Turing machine, and in simulating one step of that K-tape Turing machine, we went through several up and down moves of the head. We went through a phase which will emulate that. So similarly, one step of the behavior of M on X is what will be simulated by one phase of UTM, and it will produce exactly the same effect. So whatever was the configuration in which M started before the step is what will be on the tape of the UTM, and after one phase of behavior of UTM, which may last several steps but a finite number of steps, which definitely will finish, the configuration on the tape will be same as the similar to will represent the configuration of the machine M on X. So this is what will happen. And so we can state the following properties that the UTM will have, because UTM will mimic one step of machine M on X by several steps of UTM, but it will have the same effect. Essentially UTM will have this property. UTM, this one fixed Turing machine that Turing designed, when given a description of M and X, it will accept this code of M and X if and only if the machine M that it is trying to emulate accepts this input X. So if M accepts X, then UTM started with code of M and X will accept. If M rejects X, that is, it reaches the rejecting state after finite number of steps, UTM will reject this string, the code of M on X. And if M loops on X, then UTM will also loop on X. So it is doing nothing fancy, it is just mimicking the behavior of M on X given the description of M and X. It's a basically a program following machine. So here is a very important idea. This code of M and X, code of M, basically is called program as data. Program is being given as data to the UTM. We are coding the program as a string which is given to the Turing machine. Similarly, input we are giving as data. And the idea is that here, this UTM with this MX loaded on its tape is like a stored program computer. Any program that we want to execute, any program M, program is identified with Turing machine. Its code we can load on the input tape of the Turing machine, and then we can start executing that program. So modern day programming, modern day computers are like that. You can load any program that you write onto the memory of the computer, and then it will start executing that program, right? So the idea of stored program computer is what is being followed by this UTM. And what UTM does is nothing but it takes the code of M, the code of input, and mimics behavior of M on X, step by step. One step of this is emulated by one phase of UTM. This is what happens. Now how this emulation happens is a matter of detail. I will show you some of that detail, but it's really tedious. If you accept intellectually this is what is to be done. We have seen how basic Turing machine can emulate more complicated steps of computation. Similarly, it can also emulate the steps of computation of this M and X, where M is described to it, right? The transition table of M will be given. You will know the current configuration of M and X. You can change that configuration, right? So you can mimic the working of M on X. We'll see the details, but this is what it does. So if there is any question at this point, you can ask. I'll pause the video and then let us continue. Right. So at this point, what I want to do is I want to tell you how a Turing machine can be given as a string, as its code to UTM. So for every Turing machine M, which is the 9 tuple we saw, we will be somehow coding it as a string. Similarly, input can be coded as a string. And then we have to design this Turing machine called UTM, which will mimic behavior of M on X, right? So firstly, what is the code of M on given this? A deterministic Turing machine is basically a 9 tuple, as we said, set of states, the tape alphabet, input alphabet, the left hand marker, the blank symbol, the transition table, which gives transitions, and the start state, the accept state, and the reject state, right? This is what we saw. What we do is we arithmetize this syntax. That is, for every state, we assign a number. Suppose the set of states contains n states. That is, the cardinality of Q is n, right? The size of Q is n. Then to each state in Q, we will assign a number between 0 to n minus 1, right? So we will represent each state by its corresponding number, which is called Q hat, or the index of Q. Okay. Similarly, suppose my tape alphabet has got m symbols, then I will, to every symbol in the tape alphabet, I will assign its index, a code, number, which will be a number between 0 to m minus 1. It's called the index of A, right? So A hat denotes the number corresponding to the symbol, and Q hat gives the number corresponding to the state. And of course, the input alphabet sigma is a subset of gamma, the tape alphabet gamma. So suppose my input alphabet has size k, then I will reserve the first k number 0 to k minus 1 for the input elements of sigma, right? This is just a convention I will follow, right? So the first k indices will represent input alphabets, and the remaining indices will represent remaining tape symbols, including your left hand marker and blank and whatnot. Okay, so you can read up this description in Cozen. I will give it here quickly, right? And now this whole machine 9 tuple M can actually be written as a string over zeros and ones. So just using alphabet 0 1, I can encode this description of the Turing machine. It looks like this. First I have to tell how many states are there in my Turing machine. So since my Turing machine has n states, I will write down 0 repeated n times followed by a 1. This says that my Turing machine has n states. This is followed by 0 repeated m times followed by 1. This says that my tape alphabet has got m symbols, right? I will also give the size of the tape input alphabet. I'll say that my tape alphabet has got k symbols. So I will write down, I will give these three constants n, m and k in unary in the description. Then one of those specific states, one of those n states will be the start state, right? So suppose that start state actually corresponds to the number, its index is 3. Then I will give the code of index of 3, the start state. Start state is 3, then I will write 3 zeros followed by 1. So the number of zeros here identifies the state which denotes the start state. So I'll give the code of the start state next, which is 0 repeated index of s time. Similarly, I'll give the code of the terminal state. So I'll identify which is the terminal state, and I will identify also which is the reject state. Oh, I think the reject state is missing here. There is also code for reject state here. So right. So here there will be 0 raised to r followed by 1. Okay, code of index of r followed by 1. Then I have to identify which is my Okay, sorry, here instead of U it should be R, you know. This should be R, right? Then I must identify which is the left hand marker symbol and which is the blank symbol, which I also give. And then, so I have described everything except for this table delta, you know. And so I will then write down the code for the transition table delta, which I'll tell you what it looks like next. So first I'll describe all these elements of the Turing machine, everything other than delta. I'll write down as a string over zeros and ones, which looks like this. And then I will describe the transition table. A transition table is a list of transitions where each transition looks like this. You know, transition says that from state, you know, being in state P and reading symbol A under the head, I will change the state to Q. I will rewrite symbol A at the current cell to B, and then I'll move the tape head to the left by one step, right? Now this I can encode. This is a 5 tuple. I can encode it as the index of P, followed by the index of A, followed by index of Q, followed by index of BA, and then left I will encode as 0, right I will encode as 1. And then there will be one more one saying that, you know, this transition is over. So such a string will encode, you know, one transition, and I'll give a list of such strings encoding the available transitions in my transition table. So you can see that I can actually take this 9 tuple of a Turing machine and code it and write it down as a sequence which looks like this. Okay, so there is nothing very deep about it. It is just some slightly cumbersome encoding, but we can write down this description, you know, using symbols zeros and ones by arithmetizing the syntax. So that is what we will do. So I hope this idea is clear. Similarly, an input X, you know, which will consist of characters A, B, A, B. So depending on our alphabet, A will have a code, you know, it will have an index which was given here. So we can write down the index of, instead of this, we can write down index of A, you know, 0 to the power index of A. So we will represent A by repeating 0 index of A times, and then put a 1. Then I'll have 0 raised to the index of B, you know, 1, etc. So I can encode the input string also using zeros and ones, right? And I can separate the Turing machine description M, you know, the code of M. I can separate it from the code of X, you know, and I can give this as input to my Turing machine. This string I can give as input to my Turing machine, right? So in short, I will also abbreviate this as M hat X. Okay, this to mean the same thing. Okay, so this is the input string being given to the universal Turing machine, which gives the description of the Turing machine I am trying to simulate and the input to the Turing machine on which its behavior of M we are trying to simulate, right? So that is the idea. Now, how does UTM behave given such a string M on X? Okay, so it you know, basically UTM it's a multi-tape Turing machine with 6 tapes. Okay, and what it does is initially it, from this input code of M followed by X, it copies the code of M on tape 2, you know, because it needs to refer to this again and again. This input tape it will you know, just use for input. Then it will create the you know, this machine M has to be executed on M. What is the initial configuration of M on X? You know, it will basically be left hand marker followed by X, right? That is what will be there. And then there will be infinite sequence of blanks. Blanks we don't have to code. So what this UTM does is it takes the X part, you know, the code of X part, and copies it, you know, on tape 3. So basically tape 3 will contain this initial configuration of my Turing machine M on input X, right? This will be mimicked on tape 3. This it can copy. Then it will store the head position on tape 4. You know, if the head position is I, it will have 0 repeated I times followed by a 1 on my tape 4. So, you know, of course, initially it will be on the 0th position. So I will just have a 1 on my tape, you know, left hand marker and a 1, you know. If my head moves one step to the right, my tape 4 will look like 0, 1, because it, you know, it is now on cell 1. So that is cell 1 is position 1 is represented by repeating 0 one time. If it moves one more to the right, then I will my tape head position will look like this. So this is how I will store the head position on tape 4, and the tape head on the fourth tape will always be on the last 0. That is what we will follow. Okay, and then the current state I will store on tape 5. If my current state has index, let's say 3, then I will write 0 0 0 followed by 1 to 3 zeros to encode that my current state is state number 3. So since we have converted each state into a number, we can represent the current state as that number in unary followed by 1 on this tape 5. So this is how we will represent the current configuration of Turing machine M on input X, right? So the tape of M will be simulated on this tape 3, right? That is what we will have. And then what does the Turing machine do? Suppose M makes a move on X, that is from some configuration gamma, in one step it goes to configuration beta, right? What Turing machine will do is it will take the representation of this configuration gamma as state on tape 5, as head position on tape 4, and the content of the tape as on tape 3. It will take that, and by doing several steps of computation, it will give the description of this configuration beta of M. It will encode that. And how will it work? Basically, it will scan the tape 2, for a transition which matches the state on tape 5, because tape 5 contains the current state. So it will search through the transition table which is on tape 2 for a matching transition. The transition should also match the symbol on tape 3, right, which is at position given by tape 4. So first you take the position given by tape 4, scan the tape 3 to find the symbol at position I given by the tape 5, and that symbol is what you search for. So you can figure out which transition applies, and you make the corresponding changes. So it will transform the tape 3 content as per the transition, that it will rewrite the symbol as prescribed by the transition. It will also increment or decrement the head position by modifying the tape 4, and it will change the state to Q, by modifying the tape 5, right? So I think I have given a kind of qualitative description of how this UTM works. This UTM can be written. It's tedious to write it, but it is, I think at least intellectually it should be clear to you that such a machine can be written. And UTM is doing nothing fancy. It is just whatever moves are prescribed by this code of the machine. It is just following those one by one. It is doing mechanical calculation. For example, if you are given the expression for calculating 3 into 2 plus 4, bracketed like this, what my UTM would do is it will take as input this expression like this, find out the innermost expression, simplify the innermost expression first, so it will get 6 here, then it will simplify 6 plus 4 and give you answer 10, right? So it will, by doing this, finding out the innermost expression by moving up and down on the tape, and then simplifying it, it will do so. By doing step by step execution of the basic operations that are there, the Turing UTM will simulate the machine M on input X, right? So I hope that is clear to you. And so in one phase of this UTM mimics one step move of machine M on input X, right? That is what happens. So one phase of this UTM is used for mimicking one step move of M on X, and by repeating these phases one by one, you will mimic the run of M on X, right? And you will wind up with the same represent. Okay, by repeatedly performing this one phase action, UTM the UTM run mimics the run on X with exactly the properties that I told you before. That is, what are the properties? UTM accepts string code of M followed by code of f if and only if m accepts x. UTM rejects the code of m followed by code of x on its input tape if and only if m rejects x. And UTM loops on code of m followed by code of x if and only if m loops on x. So it is having the same outcome as my original machine and the input that I am trying to emulate. I hope you are at least intellectually aware of being able to design such a machine. I am not going to ask you to design this. Of course, UTM is a Turing machine. It should be given a string which looks like this, but you may give an arbitrary string which does not look like the code of any Turing machine followed by code of any input, right? It may be a syntactically incorrect string. In that case, UTM says that I will immediately halt and reject. So, every string which is syntactically not of this form represents a trivial Turing machine called reject. It's a one-state Turing machine which immediately rejects. It doesn't even look at its input. It just jumps on whatever symbol, the left hand marker symbol itself, it jumps to the reject state. So on every string the Turing machine will produce some outcome. Either it will halt and accept, it will halt and reject, or it will loop. And if it is given a valid description of the Turing machine and an input, then it will mimic that Turing machine. If it is given some garbage string, it will reject. This is how it behaves, right? So this is the behavior of our UTM. And I think I urge you to try to imagine what such a Turing machine would be like. I have given a qualitative description of it. Cosen also describes this in words, and you don't have to physically build this Turing machine as a UTM as a 9-tuple. That would be too cumbersome. If somebody gave me 1 lakh rupees, I would do it, but not for 10,000 rupees, right? It's just tedious, and there is nothing intellectually difficult about it. It's just lot of detail. Okay. So this can be done. So we'll assume that such a Turing machine can be designed. And in fact, Turing designed such a Turing machine, right? He basically described that such a Turing machine can be built. It's a very specific Turing machine, one model, and it's universal because it can get description of any other Turing machine and any input for that Turing machine and mimic it. So, it's in that sense, it's called the universal Turing machine. And what are the properties of this UTM? Once again, I want to emulate. UTM accepts the code of M and X if and only if the machine M, which is being coded onto the input tape of UTM, accepts the string X. So, what do we use UTM for? If you want to find out whether M will accept X or not, we will write the code of M and the code of X onto the UTM tape, and then we'll fire the UTM. And if that UTM accepts, M will accept X. If you want to check whether M rejects S, again we will do the same thing. And if UTM rejects, M will reject X. And if we fire M, we want to check whether M loops on X or not, we can never determine it. What we can do is we can give M and X in a coded form to the UTM, and UTM will also loop forever, never terminating. And if you give it some garbage input, which is not description of any Turing machine and its input, then it will immediately halt and reject. All garbage strings will be rejected by UTM. This is the behavior of UTM. So if you understand the idea of UTM, that it takes as input the code of M and code of X, and it exactly mimics the behavior of M on X, and then you are okay. This is all that you need to know. And the detailed encoding of Turing machine is given in previous 2 slides, which you can study in detail, right? But we will not need you to remember the actual physical encoding of UTM as I have given. You just have to be convinced that it can be given, right? Now, with that much background, now that we have this one, stored program computer, for Turing machines called universal Turing machine, we will make use of this, Now, remember, it's an interesting idea is being formulated here, and let me do that page after. Now you can design just as UTM is a Turing machine which takes as input code of M and code of X, right? So it takes description of my program there. You can build several Turing machines, analysis Turing machines. Turing machines, or compiler Turing machines, or optimizer Turing machines. Let's call it optimizer Turing machines. Optimizer Turing machines. What do these machines do? They take as input the description of the machine M on the input tape, and they perform a series of computations, and at the end they'll wind up with a description of another Turing machine on the tape. And this will be maybe an optimized version of the Turing machine M. It will take less number of steps to produce the answer. So, just as we have got compiler optimizers, you can have Turing machine optimizers. You give the description of the Turing machine M on the tape, and you can have an optimizer Turing machine called opt, which will intellectually, such things are possible because now you are able to compute on code of the Turing machine itself, right? So this lays possible, many kinds of analysis of Turing machines themselves to be done. Just as your compiler will analyze the program and check whether it is syntactically valid or not. If it is not syntactically valid, it will reject the program, that this is not a valid C program. So it contains some variable I which has not been declared, but it is being used. Such analysis is possible using special compiler kind of Turing machines, right? Similarly, we can analyze Turing machines. Okay, so what I will do is I will end today's lecture by defining two languages. One language is called the language MP. Okay, and let's forget about the language, and another language is called HP, right? So MP is called the membership problem language. And what does it do? It contains all code, it contains strings which represent a Turing machine and an input, but it will only contain those Turing machines and inputs on which the Turing machine M accepts X, right? So if you have code of the A raised to n, B raised to n, C raised to n. So I have code for Turing machine which accepts A raised to n, B raised to n, C raised to n, and I give it input, let us say AA, BB, CC. This will be inside MP, because this Turing machine will accept this string, right? Because it has equal number of A's and B's and C. If I give it M of A raised to n, B raised to n, C raised to n separated by string A, B, B, C, then this string will not be in my MP. This string will be in MP. Why? Because this Turing machine whose description is being given accepts this string. And so such pairs you will include in this language MP, and such pairs on which this Turing machine does not accept this string, it may loop or it may reject this string, those will not be included in MP. If you give a garbage string which does not represent any Turing machine, then of course that will not be in MP, because M will not accept X. So is the language MP clear to you? It will consist of code of all Turing machine input pairs such that M accepts X. Right? So mathematically, given any Turing machine and any input X, we know whether Turing machine accepts X or it rejects X or it loops on X. One of the three possibilities there. If M accepts X, this code M followed by code of X will be included in this language. That string will be included in this language MP. So all possible machines and all possible inputs such that M accepts X will be included in this giant language MP. Right? So is the idea of this membership problem clear? Again, I will halt here and let you ask questions. Okay. So this is also a language, right? And similarly, I will define another language called HP, which is a slight variation on that. I don't care whether M accepts X or not. I only care whether M halts on X. That is, M reaches either the accepting state T or M reaches a rejecting state R. That is, it produces an answer. It does not loop. So M halts on X is same as that M does not loop on X. Right? It either accepts X or it rejects X. So I want to include all MX pairs such that M halts on X, right? And collection of such machines. So this will not be in MP, but this will belong to HP. On the other hand, if I had a Turing machine which does not halt on certain input strings, those will not be included in HP. So I have these two languages, MP and HP, that I have defined. And they also use this idea of coding, a machine by a string and coding input to the machine by a string and giving those codes. So this is language of codes, and MP is a collection of strings representing this such MX pairs. HP is a collection of MX pairs representing this having this property. So these are the two languages that we have. Okay. Now these languages played very important role, in studying, answering those philosophical questions about, are there RE languages which are not recursive, why do we need Turing machines which don't halt but still compute answers in good cases, etc. Right? So the key questions we want to answer is that first thing to realize is that both MP and HP as languages are RE languages. That is, there are Turing machines which will accept exactly the strings which belong to MP, and there are Turing machines which exactly accept the strings which belong to HP. Now I'm going to pause here and ask somebody, do you know any Turing machine which will accept the elements of MP? Okay, so my claim is that if you consider the language of universal Turing machine itself, that language is same as MP. After all, what does the universal Turing machine do? On input M and X, it mimics the behavior of M on X. And if M accepts X, then my UTM will accept the pair MX, right? So this pair MX will belong to the language of UTM if and only if M accepts X. And if M rejects X, that pair will not be accepted by UTM, so it will not belong to the language of UTM. And if M loops on X, again it will not be accepted by UTM, a UTM will loop on it, and hence this MX pair will not be in this. So you can see very easily, just work this out yourself in your head, that the language of UTM is actually this language MP that I have defined here, right? So I already have a Turing machine which accepts MP, and this Turing machine doesn't halt on every string. On those Turing machines with loop on X, UTM will also loop. So it's not a total Turing machine. It's a partial Turing machine, right? So we know that MP is RE because there exists a Turing machine recognizing exactly the language MP. What about HP? Well, we can construct another Turing machine which we shall call as HTM, by slightly modifying this machine UTM. We have already built this UTM machine, we will change it little bit. We'll do surgery on the UTM and construct another machine called HTM, whose language will be HP. What do we do? In HTM should recognize all those MX pairs such that M halts on X, whether it accepts or rejects, but it should halt. For that, what do? We look in UTM, all transitions which go to T, we will let it go to T in HTM. All transitions of UTM which go to R, in HTM we will redirect them to go to T. So whether the UTM accepts or rejects, HTM will accept. But whenever UTM loops, HTM will loop. So HTM has only two possibilities, either it will accept or it will loop. And what will be the language of this UTM that we have constructed? All those strings on which UTM halts, that is, it goes to R or T, HTM will go to its T, and so it will accept. So all strings on which M halts on X will be accepted by HTM, so its language is exactly HP. So what I have convinced you is that language MP and HP are both recursively enumerable, and we can actually physically build two Turing machines which will accept these languages. The code of MX and such that M accepts X, and the code MX such that M halts on X, right? I think this is all I want to do in today's lecture. There are many, none of the ideas are, extremely involved, but there is a certain amount of abstraction, a certain amount of coding going on. So I urge you to study this slides and come for next class. In the next class, we are going to answer a critical question, which is, are these languages MP and HP recursive? Can there be a total Turing machine which can accept MP, that is, which can determine whether M accepts X or not? So, or whether M halts or not, because there are some bad strings on which some partial Turing machines do not halt. Can we analyze this using another Turing machine? So the question we want to ask is, are these languages MP and HP recursive? Are MP and HP recursive? And this is not a very straightforward answer to give. It will take us whole of the next lecture to answer. So I think I will end with this and let you ask questions. Thank you.